Section 7.2, question E32, and we have heights of males and heights of females that are given. I've put them already over here in a small Excel table. And what we're really looking at here is what happens when we make selections from different populations. How does that affect our expected mean and standard deviation and so forth? So we select one male from this age group and one female, and we're going to add the two heights. What is the expected mean that we'll get? Well, the mean isn't too bad, so I'm going to put here one male, one female. So the most likely, or the best prediction we can get of the male is 69.4, and the best for the female is 64.1 if we're just selecting a single one. Actually, if we're selecting even more than one. So what happens is we just add the expected values. In other words, the mean of all the different times where we would select one male and one female is going to be the same as adding selection of one male to adding a selection of one female. So expected values you can just add or subtract as you would normally. So that's going to give us a 133.5 mean for that double selection. Standard deviation is not so simple. We cannot just add or average, for that matter, standard deviations. In other words, if we did the same thing here, adding these two standard deviations, we get 5.67, which is clearly more than what's given here. So what's going on there? Although we can't add standard deviations, we can add variance. Variance is linear, and so let's get the population variance for each of these groups. Well, how would we find that since we don't have all the things we need for the typical formula for variance? Well, we know that the relationship between variance and standard deviation is that variance is standard deviation squared. So let's take advantage of that, and we're just going to take this caret 2, and that'll give us the variance for the population of each of these groups. And now we can get the overall variance adding these together. So I'm going to do that real quick. So that 16.0889 is the variance for this method of selecting one of each. And now we can go backwards and get the standard deviation by taking the square root of the variance, and that gives us our 4.01. So again, means and variances from separate populations can simply be added. Standard deviations cannot, but using the knowledge that we have of the connection between standard deviation and variance, we can go backwards then to get that population standard deviation. Okay, find the probability that the sum of the heights is less than 125 inches. So we know now that we're looking at this group where the mean is 133 and we have a standard deviation. So let's use our concept of the z-score by taking the normal distribution and taking the x value, so that 125 is the specific number we're interested in, the mean, which is right here, and the standard deviation, which is right here. We do want cumulative, and we get 0.0170. Now, you may wonder, why didn't we use that adjustment where we take the standard deviation divided by the square root of n, so the square root of 2 in this case, since we have 2 people? Well, because these numbers right here reflect this single method, I guess, of one male and one female. So of all the times we would choose one male and one female, this is the mean we're going to get, this is the standard deviation. So we actually have the data for that population of these samples of using this method. In other words, this is the parameter itself for that method. And so since this is the parameter, when we're taking one of each, we're just taking a single unit from this population of one male, one female. Now, if we took 2 males and 2 females, then yes, absolutely, we would divide by square root of 2 in this case. But because we're just taking a single unit in this population, we can use the original z-score calculation. Okay, what total heights are reasonably likely? Now this is kind of ambiguous. So what they're really saying here is, what's the chance we'll get it within 2 standard deviations of the mean, or either way. So let's first do the low end. Let's take the mean minus 2 times the standard deviation, and that's going to give us 125.47, and that's not matching up quite with what they have, and I'll show you why in just a second. So here we're also going to take the mean plus 2 times the standard deviation, and that's going to be a little higher than what they have. Why is that? Well, what we did right there is we put a 2 standard deviation window around the mean, which is nice because 2 is an even number to remember. However, another way to do this is by using a 95% interval. In other words, we want 95% of the data to fall within our range. If we want to do that, we're slightly off of 2. So the numbers we have to use here are 1.96, and here, oops, okay, sorry about that. Here we're also going to change this 2 to 1.96, and these will give us the numbers that match up with what Wiley is using. So again, what's the discrepancy there? And my point is that either of these are okay. You can either use a nice whole number of 2 standard deviations to the left and right of the mean, or you can create the interval so that it'll capture exactly 95% of the data, because 95% is a nice round number that's typically used. But if we do that, we're going to be 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. Either of those are acceptable both in this class and in practice. And what is the probability that the male is at least 2 inches taller than the female? Okay, so we need the male to be at least 2 inches taller. What we're going to do now is we're going to take a male and female, and we're going to subtract the 2. So what would be our mean of, Okay, sorry there. That was a call from my doctor telling me the results of some tests that my vitamin D was low. So just out of curiosity, what am I going to do? As soon as I get done with this screencast, I'm going to go look at what my actual results are. I'm going to look at what the recommended mean and standard deviation is, and I'm going to look at how far off of the mean I am. So it's a good example of statistics in use here. I can kind of estimate whether I'm extremely low in vitamin D or whether I'm just moderately low, and that can help me make some decisions respectively. Okay, so back to this. What we're looking at now is male minus female. For the population mean, this is fairly straightforward, where we just take the average male minus the average female. The variance is a little bit harder to understand, I guess, because we have the variance of this and we have the variance of this. It might make sense that we subtract it just like we did the mean, but it doesn't quite work that way. One way to think of it is variance is this enemy that you're fighting against, and you can't just take away from it by simple subtraction. It's going to build no matter how you combine your one from this and your one from this, because we're expecting that there will be variance here and there will be variance here. So in fact, what we do is we add them just as we had done. Oops. Okay. So here I extrapolated a formula a little too far. I actually want B12 and C12. Okay, and that should give me the 16.09 again. So I'm going to have the same standard deviation and variance whether I add the two or subtract the two. And maybe really I should, for greater accuracy, write it like that. So the mean will be different depending on whether I add or subtract them. The variance will stay the same. So the question is, what's the probability the male is at least 2 inches taller than the female? So in other words, what's the chance that this m minus f is at least 2? So we can do that again with our normal distribution. And our x value here is 2, is what we're looking for. 2 inches. We want to know when m minus f is at least 2. And we have our mean, our standard deviation, and this gives us 0.20. Again, it's well off of this value. What's happening? Well, we want to know the male is at least 2 inches taller. So this 0.205 tells us that 20.5% of the units from this population would be less than 2 inches taller. So all we need to do then is subtract this number from 1, and we get 0.7946.